right, in this lesson we're going to add a few more postulates and theorems, and then you're going to use that to solve for unknown angles with parallel lines cut by a transversal. So first, a few definitions. Parallel lines are parallel when they are coplanar and never intersect. So coplanar means that they lie in the same plane. You can put a flat surface on them. So if they are coplanar and they never intersect, this could be line L, this could be line M, then L is going to be parallel to M. The double, like the stretchy 11, the double lines here is a symbol for parallel. Now in three-dimensional space, we also have something called skew lines. Skew lines are non-coplanar, and they also never intersect. So if I were to try to draw this, if this were a plane and line L is in the plane, I could have line M coming out of the plane, and they don't intersect. Those lines would be skew. Okay, we have two postulates we're going to write down. And remember, postulates are statements that are just accepted to be true, because you can't really prove them. They're just accepted, okay? The first one is called the parallel postulate. Okay, here it is. Given a point not on a line, there is only one line that passes through that point and is parallel to the given line. So if I were to draw this, and again, that's the parallel postulate. If I have line L, and I have a point P that's not on line L, the parallel postulate says there can only be one line that passes through point P that's going to be parallel to L. Okay, there can be an infinite number of lines passing through point P, but there's only going to be one that's going to be parallel to L. That is the parallel postulate. Okay, the perpendicular postulate is similar to the parallel postulate. Okay, and it says given a point not on a line, there is exactly one line passing through that point perpendicular to the given line. So it's like the parallel postulate, only now we're talking about perpendicularity. So if I have line L and I have a point P, I can only have one line passing through point P perpendicular to L. Okay, if I called that M, I could say M is perpendicular to L. So this is our symbol for perpendicular. It's the upside down capital T. So now we're going to look at parallel lines cut by a transversal. Here's what that looks like. If I have lines that are parallel, so that's L, that's M. I can say L is parallel to M. My transversal line is the one that cuts across both of them. Okay? And in this setup, we'll have a series of angles. If I number all the angles, and I say 1, 2, 3, 4, 5, 6, 7, 8. I have 8 angles, but really there's only going to be 2 different answers that I have in here. And we're going to start with a postulate, and we're going to define what corresponding angles, a property of corresponding angles. So first of all, corresponding angles are angles that are in the same general location. So 2 and 6, 1 and 5, 4 and 8, 3 and 7. Those are our pairs of corresponding angles. So if I go 1 and 5, 2 and 6, and then 2 more, 1 and 5, 2 and 6, 4 and 8, and 3 and 7. All of those are corresponding angles because they are in the same relative location. So we're going to start off with another postulate here. Again, this is something that doesn't have to be proven. We're just going to accept it to be true, and then we're going to prove a few other things. So here's the postulate we're starting with. If parallel lines are cut by a transversal, then corresponding angles are equal in measure, or corresponding angles are congruent. So we can use this to prove other properties and other theorems in our setup here. Okay, so we are given that L is parallel to M. So I drew two lines. I've got parallel lines cut by a transversal. L is parallel to M. We're given that. I want to prove that the measure of angle A is equal to the measure of angle D. Okay? So we're going to use our postulates and theorems and properties to figure this out. So here's how we start. Again, we start with our given. L is parallel to M. We always write our given down. And then let's take a look at this. I want to, well, if I put in another angle, because I don't know anything about these alternate interior angles, which we're going to get to some labels in a minute, but if I put in the corresponding angles, so if I put in an E up here, I know that E is going to be congruent to D. So let's write a statement about that. I can say that the measure of angle E is equal to the measure of angle D. And that is because corresponding angles, so here we can abbreviate, corresponding angles are equal. Okay, equal or congruent, you could say either one. Okay, but I'm going to stick with equality because I'm talking about measurements. All right, so then what we look at is, well, what else do we know? We know that E and B are supplementary because they are linear pairs, and A and B are supplementary because they are linear pairs. So we can write something like that. We can say angle E and angle B are sup, because you can abbreviate. And the same line, you can say angle A and angle B are sup. And you can say linear pairs are supplementary. Oops. I haven't used that one yet. Whoops, gotta erase it. Linear pairs are supplementary, or angles on a line, two angles on a line are supplementary. Either way. Okay. All right, so in our last lesson we learned that if two angles are supplementary to the same angle, then they are equal to each other. So this is where I can use that. I can now say that the measure of angle A is equal to the measure of angle E. Supplements of the same angle are equal. And I can do all that abbreviating, okay? So here's what I have. I have the measure of angle A equals the measure of angle E, and I have the measure of angle E equals the measure of angle D. Well, when two things are equal to the same thing, they are equal to each other, and that's substitution. So that's the end of my proof. It really doesn't take long. The measure of angle A is equal to the measure of angle D. And my reason is substitution. Okay? So what we've just proven is another theorem that we can now use. And that theorem, we've proven that when the lines are cut by a transversal, that these angles here are going to be equal. Now you could do the same thing with the other angles because the location of E is arbitrary. It could be over here. You could have said these two corresponding angles are equal, and then these are supplementary, or these are supplementary, and you could have the same thing, okay? Either way, we call these angles alternate interior angles. So we've just proven that if parallel lines are cut by a transversal, alternate interior angles are equal. And this is the only time we're going to write this all out. Okay, alternate interior angles are equal. Equal in measure. Okay. All right, so we just proved that theorem. And we're going to take a look at same side interior next. Okay, so here's our next one. We have our parallel lines. L is parallel to M. They are cut by a transversal. I have angle A and angle B. These are called same side interior angles. So I want to prove that A and B are going to add to 180. I want to prove that they're supplementary. So we start off with our given. L is parallel to M. That's our given. And then again, we can start with corresponding angles. If I put an angle C up here, I know that C and B are going to be equal to each other. So I can write that down. So the measure of angle C is equal to the measure of angle B. Corresponding angles are equal. So notice how I abbreviated this. I abbreviated corresponding. I used the angle symbol. I said are equal, and I didn't put down the whole if parallel lines are cut by a transversal, blah, 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 blah. You don't have to do that. I've graded these for years and years and years, and abbreviating these statements is just fine. Okay? So now let's take a look. A and C add to 180. So we're going to do that. A and C add to 180 because linear pairs add to 180. Okay, so I could say the measure of angle A plus the measure of angle C is equal to 180 because linear pairs add to 180. Angles on a line add to 180. Either way would be acceptable there. Okay, so let's see. I have these two add to 180. I have C equal to B. So if I substitute in here, I'm going to get the fact that A and B are going to be equal to 180. So let's do that. By substitution, the measure of angle A plus the measure of angle B is equal to 180. So that is substitution. And then this is essentially the definition of supplementary. So at the end, your final statement will be angle A and angle B are supplementary. And the reason is going to be definition of supplementary. So here's what it looks like. Angle A and angle B are supplementary. We always end with what we're trying to prove. Definition of supplementary angles. And look how I abbreviated that. DEF, sup, angles. That's totally okay. So the theorem that was just proven is if parallel lines are cut by a transversal, this will be the only time we write it out. Then same side interior angles are supplementary. Same side interior angles are supplementary. And those are our theorems for working with parallel lines. Again, you don't have to prove these yet. I'm doing these proofs so you start to see how they work and you start to understand the structure and the patterns to them. But what you're going to be focused on is just finding unknown angles with parallel lines cut by a transversal. So it's not quite as complicated as this. I'm going to work a couple of examples here for you. Okay, this is example number 14 on page 156. You don't have to redraw this if you don't want to. You can look at the picture, the diagram in the book, because the actual problem takes less time than to draw the picture, I think. When I have arrows on the lines here, that means those two lines are parallel. So we have parallel lines, we have a transversal here, we have a perpendicular transversal here. It's kind of a complicated diagram for actually what we're trying to find. Angle FPM is 34 degrees, FPM. So angle FPM is 34 degrees, and all we want to find is the measure of angle NMP. So if we look, NMP it's going to be on the other side here. It's going to be there. Well, these are alternate interior angles because here's our parallel line and here's our transversal. So in the end, that angle has to be 34 degrees. Okay, we're going to do one more example here. So in this diagram, I have my two parallel lines, I have my transversal, and each angle is just labeled with letters A, B, C, D, E, F, G, H. All right, so in this problem, the measure of angle B is 4 times the measure of angle A, and we want to know what is the measure of angle F. So this drawing is not to scale. It almost looks like they're 90 degrees, and that's not what this is. Angle B is 4 times the measure of angle A. So I don't know anything about the measure of angle A. So we'll let X equal the measure of angle A. So that means 4X has to be the measure of angle B. And then when you look at the picture, A and B are going to add to 180 because they are a linear pair. So you do that next. You're going to say the measure of angle A plus the measure of angle B is equal to 180. So if I wrote that equation, 4x plus x is equal to 180. And then we solve it. 5x is 180. And you have x is going to be 36. So then when you take the 36 and go back up to the let statement, when you go back up here, A is 36, B is going to be 144 because they got to add to 180. And then when you look at the diagram, B and F are corresponding angles. Therefore, the measure of angle F is 144. So we will look at these properties and some more examples in class to show you how to use these theorems to solve for unknown angles with parallel lines.